In this chapter, we'll study kinetic energy, work, and principle of work and energy applied to rigid bodies. This chapter is we have seen something similar with particle, where we have studied about kinetic energy, work, and principle of work and energy for particles, but now this time it's applied to rigid bodies. So let's quickly revise what we have studied for particle. So you are familiar with this equation, work and energy principle applied to particles. So where T1 is the initial kinetic energy of the particle, which is 1/2 mv square, sigma u 12 is sum of the work done by all the forces acting on the particle, is equal to final kinetic energy of the particle, which is again 1/2 mv square, but this time it's v2, that is final velocity. And in this equation, we have seen that the sigma u term can include work done by different forces, such as work done by externally applied force, where it's force integral of force and this product of force and displacement. If under the effect of this force, particle moves from position S1 to S2, then this integration F cosine theta ds gives us the work done by the applied force. And we have also studied that work done by the force is positive if the force and the displacement are in the same direction. If they are in opposite direction, then the work done is negative. Second is we have studied about work done by weight in case of particles, and that's negative here. So work done is negative if the particle moves from low elevation to high elevation, but if it is positive if the particle moves from higher elevation to lower elevation. So this is work done by weight or work done by gravity. And third is if the rigid body or particles have like spring elements connected to them, then work done of a spring, which is opposite force and displacement, can be given by this equation, where remember it's a negative sign here, and it's 1/2 k s2 square minus 1/2 k s1 square, where k is spring constant or stiffness of the spring, and s2 and s1 are the final and initial displacement of the particle attached to the spring. Okay, so if the spring force and the displacement are in the same direction, then this will be a positive number. If they are in opposite direction, then this will be a negative number. So this is, I think we have studied this in chapter 14, so this is known to you. Now what we need to do is we just need to extend this concept and apply to rigid bodies rather than particles. But for that, remember always the difference between particle and a rigid body, that a particle does not have a shape and size, but it has mass, while rigid body has shape, size, and mass. So rigid body can have rotation about its center of mass, which is not possible for particle. Now we can consider the golf ball as a particle in this slide. For example, when a player applies the force on the golf ball using the club, then the club does some work on the ball, and that changes the kinetic energy of the ball, which we can calculate by applying the work energy principle. But in this example, for example, the game of bowling, we need to consider the ball as a rigid body rather than particle. Now when a person throws the ball on the track and it goes towards the pin, the ball has two different types of energy. It not just have only kinetic energy, but it also has the energy because of its rotation about its own mass center. So ball rotates on its own axis or on its own mass center when it travels from this end of the track to the other end. So when we say ball has certain kinetic energy, which point is our reference point on the ball? So we attach this velocity to the mass center of the ball. That's why in our equation we have Vg, where V is the velocity and G is the mass center of the ball. So this ball has the energy, total kinetic energy is 1/2 mvg square, which is translation kinetic energy, same as particles, plus it has this additional term which was absent in particle, which is 1/2 ig omega square, where ig is the mass moment of inertia of the ball with respect to its own mass center, and omega is the angular velocity with which ball spins while it travels linearly on the track. Okay. These are some of the YouTube links. You can also just search on YouTube about like bowling slow motion, and you will see how the ball rolls on its mass center while it travels on the track. So let's start with the quiz. So kinetic energy due to rotation of the body is defined as 1 half mvg square plus 1 half ig omega square. So the correct answer is answer B. Uh, well, it depends on which, this is, I personally believe it's not completely correct answer. The only reason is because we do not know what is the point of rotation. Because if the rigid body is rotated, is in pure rotation, and it's with respect to its own mass center only, then the correct answer would be 1 half ig omega square. But if the body rotates about a point which is not its mass center, then this is the correct answer, 1 half mvg square plus 1 half ig omega square. You will see this shortly during the presentation. And this question is about the work done by forces. So when calculating work done by forces, the work of internal force does not have to be considered because uh, they are equal in magnitude but opposite in direction. So the work done by internal forces cancel out. So basically that's why we don't consider the work done by internal forces. Okay, so these two are two quizzes. Okay, now for the next few slides, we'll talk about the applications of rigid body, applications of principle of work and energy for rigid bodies. So consider this concrete mixture. It consists of this big drum, which is driven by this gear, which in turn is driven by the smaller gear. We call it pinion, and the pinion is driven by electric motor. So if we know the RPM of the electric motor, that is rotations per minute or angular speed of the electric motor, if we know the size of the gears, that is if we know the number of teeth on both the gears, then we can calculate the rotational kinetic energy supplied by the electric motor to the drum. Okay, and so that's the question here. So if the motor gear characteristics are known, how would you find the rotational velocity of the mixing drum? So we can do that provided that we know the gear ratio and we know the angular speed of the motor. Second application is the soil compactor has an engine. So this engine delivers the power which rotates these wheels as well as it gives the translation kinetic energy to the frame. Now this translational kinetic energy is supplied to the roller, which not only rotates but it also translates, so it has both rotational kinetic energy and translation kinetic energy. So are the kinetic energies of the frame and the roller related to each other? If so, how? So they both are related to the same equation that we have seen in case of the bowling ball, that the total kinetic energy of the rotational drum is nothing but the linear kinetic energy of the frame plus rotational kinetic energy of the drum, which is 1 half I omega square. So this is the equation we'll use for rigid body. So the kinetic energy of rigid body, this is the generalized equation, is combination of translation and rotational kinetic energies. So T is equal to 1 half mvg square plus 1 half ig omega square. Now depending on the type of motion of the rigid body, whether it's translation, pure rotation or general plane motion, some of the terms in this equation will be present and others we do not have to consider. For example, consider this rigid body which is in pure translation. So this just moves in linear direction. It does not rotate with respect to its mass center or any other point on the rigid body or outside the rigid body. That means this omega is 0. So this rigid body has only pure translation kinetic energy, which is 1 half mvg square. Okay, because omega is 0, it's pure translation. Now consider this example where the rigid body is in pure rotation. Now there are two different cases. If the rigid body rotates with respect to its mass center, So if you assume that the body does not rotate from point O, but let's say it rotates from point G, and then it's in pure rotation, so it does not translate, but it just simply rotates with respect to point G, then its kinetic energy is 1 half, which is zero point 0.5 Ig omega square, where Ig is the mass moment of inertia of the rigid body with respect to its mass center, and omega is the angular velocity of the rigid body. But for the same rigid body, if it rotates with respect to an arbitrary point O, which is some distance away from its mass center, then this rigid body has both two terms in its kinetic energy. One is 1 half Ig omega square plus second term is 1 half m Vg square, where Vg is the linear velocity of the body's mass center. Okay, and if we know this distance between point O and G, let's call this distance r, then this velocity is nothing but omega r. So it's the product of angular velocity and the radius vector. Okay, so it's r omega. So Vg is rg omega. So in this equation, if we substitute Vg is equal to rg omega, and then if we simplify the equation, we will have a single term in kinetic energy, which is 1 half I o omega square, where Io is the mass moment of inertia of rigid body with respect to point O. So in a way, if I need to make a generalized statement for rigid body in pure rotation, I would say that kinetic energy is always 1 half I omega square, where I is the mass moment of inertia about the point of rotation. If the point of rotation is G, then it's Ig omega square. If the point of rotation is O, then it's Io omega square. This slide explains about the work done by different forces on rigid body. This I have already explained in case of particles, so I skip this part. Now, some forces in rigid bodies, they do not do work. So this slide is about those forces which are present but they do not do work. So what are those forces? So those forces are normal force and friction force. They act on the body, but they do not do work because there is no instantaneous displacement of the point in contact with the ground. So this point here, instantaneous center of zero velocity at the given instant, that means if you take the snapshot, these forces, they do not result in any displacement of this point. Okay, so that's why there is no displacement, no work done, because work done is the product of force and displacement. So displacement is zero, then work done is zero. Similarly, we do not consider internal forces because they are equal in magnitude and opposite in direction. This was actually the question 2 in your quiz at the beginning of the slide. So the work done by this force is zero. So in short, if I need to summarize this slide, I would say that normal force and friction force and internal forces, they are not considered for the work done. That's it. Now this slide is very useful because this is something unique for rigid body which was not present for particles. I keep on saying always that particles do not have, like we do not consider the size of the particle. That means particles cannot have rotation about its mass center. Okay. While rigid body can have rotation about its mass center. So if this rigid body is subjected to couple moment, that means if there are two equal and opposite forces applied at some distance away from the point of rotation, then this forces results in couple moment acting on the body about point O. That means we need to consider the work done by couple moment, and this work done is given by um, which is integral of product of moment and displacement, angular displacement from angle theta 1 to theta 2. In other words, if these forces are applied on a rigid body, and as a result of these forces, if the rigid body changes its angle from theta 1 to theta 2, then the work done by couple moment can be calculated using this equation. You can actually compare this equation to this equation. It's very similar to this equation, that it's now force into linear displacement for rigid body because it has rotation, it's moment into angular displacement. between theta 1 and theta 2. Now, if this couple moment is constant, that means it is not the function of time, or it's not the function of theta, then it can be taken out of the integral, and then this is just the integral of theta 1 and theta 2 with respect d theta. So it's m theta 2 minus theta 1. But if m is function of theta or function of time, then it cannot be taken out of the integral. It has to stay inside the integral, and we need to proceed with the integration. Now, the work done by the moment is positive if moment and angular displacement are in the same direction. And if they are in opposite direction, then work done by the couple moment is negative. This is very similar to work done by forces, where work done by forces is positive if force and displacement are in the same direction, and it's negative otherwise. So this is the final equation for work and energy for rigid body. It's the same equation that we have used for particle, in fact, that initial kinetic energy plus work done by all the forces is equal to final kinetic energy. Now, some things to remember here for when you solve the problem for rigid body is kinetic energy is not always 1/2 mv square, but it can include 1/2 I omega square, depending on the type of the motion. And the second thing that you should remember is that in equation of work done by forces, you need to include externally applied force, weight or gravity, and the third one is spring force. And most important is you also need to account the work done by couple moment, this equation that we have just seen. Okay? So that's the difference between particle and rigid body. Otherwise, the procedure to solve the problem is very similar between the particles and rigid body. So now, based on this much information, let's consider this example where there are two cylinders. They both have the same mass, and they are kept at certain height h on the ramp, and then they are allowed to roll freely under the effect of gravity. What do you think that which cylinder will win the race, or which one will have higher velocity or higher speed when it reaches the bottom of the ramp? Solid cylinder or hollow cylinder? I repeat the question, they both have the same mass. There is no difference in mass. They both are at the same height. They both are released at the same time. The only difference is that one of them is solid, another one is a hollow cylinder. And we need to calculate their speed at the bottom of the ramp. You can pause the video, you can think about the answer, and then you can proceed. So I give you the answer now. And the answer lies here. So when the cylinders are at the top, they have potential energy, which is mgh. And when they come at the bottom of the ramp, they have kinetic energy, which is 1/2 mv square. But for rigid body, we also need to consider the energy because of the rotational motion, that is 1/2 I omega square. So if you do this math, I'm not going through this derivation, for both the bodies, then at some point you will get this equation. Till now, everything is same for both the objects. So 2mg m plus n, this is moment of inertia, and r is the radius of the cylinder square, and everything is fine. Now, at this point, we need to substitute the equation of mass moment of inertia. For cylinder, this is the equation sheet for different mass moment of inertia. For cylinder rotating with respect to its z-axis or axis passing through its center, its mass moment of inertia is 1/2 mr square if it is solid cylinder. But if it is hollow cylinder, and we assume, if we consider this is a thin ring, then its moment of inertia is mr square. So that's the difference. This is mr square, and this is 1/2 mr square.